Hello friends, welcome to this video on set theory, which will be talking about how to represent a relation in the form of matrices. Matrices as such is going to be the easiest way of representing a collection of elements. And let us now see how we can represent the relation as matrices in this 9th video of the series set theory. Come on, we will move into the video. Matrix of a relation R. Let R be a relation from the set A, which has the collection A1, A2 up to AN, to B, which has B1, B2 up to Bm. The matrix representation of the relation is represented by the script MR, and the matrix Mij has just the collection of elements 1s and 0s. The matrix entry is taken as 1 if the ordered pair Ai, Bj belongs to the relation, and it takes the value 0 if the ordered pair does not belong to the relation. Now, let us say, for example, if A is going to be the set that contains A1, A2, A3, and B be the set that comprises of B1, B2, B3, and B4. Let R be the relation which has been defined from A to B as A1, B2, A2, B3, A3, B2, and A3, B4. Now, let us form what is going to be the matrix of this relation called as R. So, how to frame my MR? My MR is from A to B. So my rows are taken as A1, A2, A3, and my column to which my A's are marked are my B1, B2, B3, and B4. So this is going to be the structure of the matrix which I have to fill. So it is going to be a 3 cross 4 matrix. The matrix is filled using the law that the value is taken as 1 if the ordered pair belongs to the relation and 0 if it does not. So now for all the entries inside the relation, let us mark the matrix entry as 1. So the first entry will be for A1, B2. This takes the value 1. The next entry is for A2, B3. A2, B3 takes it as 1. Next A3, B2. A3, B2. This takes as 1. And last is A3, B4. A3, B4. This is going to be 1. So for the relations over here, we have the marked entry as 1. And the entry is going to be 0 for all the ordered pair that doesn't belong to the relation. So we may mark the remaining positions over here with zeros. So matrix which is obtained in this format, MR, is going to represent the relation R which has been presented here. We will take it with one more example. If R is the relation on A, 1, 2, 3 such that A, B belongs to R if and only if A plus B is odd, find MR, MR inverse, and MR complement. Now we have been given a law or rule by which this matrix has to be formed. So first I need the relation R which has been defined on my set A. So what will be the collection of elements that is going to give me odd when added? So it is from A which is going to be 1, 2, 3 to the set A itself which is going to be 1, 2, 3. So the first odd number to be present is going to be 1, 2, and next 1, 3 will be 4, 2, 1 will be an odd number, 2, 3 will be an odd number, 3, 2 will be an odd number, and that's it. So if I am going to represent this matrix as a relation, I have 1, 2, 3 marked here against the 1, 2, 3 to which it is being mapped to. 1, 1 is going to be 2 which is not odd, so this is 0. So the first entry 1, 2 takes the value 1. Next entry is 2, 1 which takes the value 1, and 2, 3 which takes the value 1. So this becomes 0 because 3 plus 1 is 4, an even number. 2 plus 2 is 4, an even number. 3 plus 1 is 4, an even number. And 3 plus 3 is 6 which is an even number. And 3 plus 2 is 5 which is an odd number. So I give this as 1. So this is going to be the matrix of the required relation. And what is the relation? A plus B is going to be an odd number. So now we will move on to find what is going to be the second requirement of us, which is going to be MR inverse. So how do we define the inverse of an relation? If R is going to be a relation A comma B such that A belongs to your capital set A and B belongs to your capital B, then your R inverse is the set of ordered pair B comma A such that B belongs to your capital B and A belongs to your capital A. Any guess how we can get your inverse? So what is happening over here? A comma B becomes B comma A. So there is going to be a shift in the position. How we are shifting? Just take your MR and then take the transpose of it. What do we mean by a transpose? Transpose of a matrix is shifting a row to a column and a column to a row. So what do we do is, we make the first row 0, 1, 0 to become the column 0, 1, 0. The second row now becomes my second column 1, 0, 1. The third row now becomes my third column 0, 1, 0. We see that the matrix after getting transposed still looks to be the same as a original matrix MR. So what do we mean by it? We notice that above and below the diagonal, the elements are going to be the reflections of one another. That is, what we have is going to be a symmetric matrix. For a symmetric matrix, the MR and its MR transpose, that is A and A transpose, looks the same. But it will not always be the same for the cases of all the relations R. For our problem, it happened to be the same. So how to find the inverse? The inverse is got by transposing your rows to column and columns to rows. Next we will move to MR complement. So what do we mean by MR complement? So what is going to be my complement of a relation? Complement of a set we will first see. What do you mean by complement of a set, which is denoted by A bar? It is nothing but elements that are going to be in your universal set but that are not going to be in your A. So from your universal set, you remove all the elements of A. What you get is going to be your complement set A bar. Similarly, how to get your complement of a relation? So what is equivalent to our universal set over here? Our Cartesian product A cross B is something equivalent to our universal set. From this Cartesian product, you remove all the elements of the relation R, and now the left out value will be your complement of your relation. What was my A over here? A was 1, 2, 3. So if A is going to be 1, 2, 3, what will be my A cross A? It is 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. So from this, what I did do, I need to remove my elements of relation. And what are they? 1, 2. So 1, 2 is striked off. Next is 2, 1 and 2, 3. 2, 1, 2, 3 is striked off. And next is going to be 3, 2, you strike off. So what is left out is going to be 1, 1, 1, 3, 2, 2, 3, 1 and 3, 3. So in this position, now I am going to mark them as 1. So I 1, 2, 3 with 1, 2, 3. What do I have? Is going to be 1, 1 in the relation, 1, 3 in the relation, 2, 2 in the relation, 3, 1 and 3, 3. And the remaining positions are marked as 0. This may look a little complicated at first sight, but there is a trick to find what is your MR complement. So the best and easiest way to get your MR complement is that we notice that wherever we had our 0 in the original value, we are getting this to be 1. which means the values have now been replaced with the complement of it. So how to get the complement? Wherever you have 1, flip it as 0, and wherever you have 0, flip it as 1. In which case you can easily get the value for the complement. Be careful, friends. For sure, there will always be a little slip between the symbols called as complement and inverse. What do you do in inverse? In inverse, we transpose rows to column, columns to rows. In our complement, we flip ones to zeros and zeros to 1. So be a little attentive when you attend a problem on complement and inverse. We move on to the next set of problems where we have M are to be one relation given as a matrix and M is to be one relation given as a matrix. We have been asked to find R union S, intersection S, product S and R square. Let us first begin with M of R union S. What is meant by union? Union is our OR operator. If either one of your R or your S has a 1, then you can mark the entry in the union as 1. If both of them are going to have zeros, then the entry becomes 0. Or if any one of them is 1 or both of them is going to be 1, then the matrix entry is going to be 1. This is going to be the rules for your OR. So for this OR operator, we are now going to check 1, 1. One of them is 1, so you take the answer as 1. 0, 0. Both of them are 0, so the answer is 0. 1, 1. So the answer is 1. 0, 1. Any one of them is 1, so the answer is 1. 1, 0. Any one of them is 1, answer is 1. 1, 0. Any one of them is 1, answer is 1. 1, 0. Any one of them is 1, answer is 1. 0, 1. Any one of them is 1, so answer is 1. 0, 0. Both of them are 0, so the entry is 0. So this is my R union S. Next we move to R intersection S. What is this intersection? It is nothing but our AND operator. What does our AND operator say? If both the entries are 1 and 1, then the entry is 1. In all the other remaining cases, the entries become 0. So keeping this rule in mind, we now check 1, 1, the entry is 1 because both 1. 0, 0, the answer is 0. 1, 1, the entry is 1. 0, 1, only one of them is 1, but we need both of them as 1, so the entry automatically becomes 0. 1, 0, so it is 0. 1, 0, it is 0. 1, 0, it is 0. 0, 1, it is going to be 0. And 0, 0, it is going to be 0. So we have the R intersection S to be of this format. Next, what we need is the product of R and S. So let us quickly recollect how to go about multiplication of matrices. Our MR is 1, 0, 1, 0, 1, 1, 1, 0, 0. And our MS, using which we are taking the dot, is going to be my dot, my MS is going to be 1, 0, 1, 1, 0, 0, 0, 1, 0. Let me check it one more time. 1, 0, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 0, 0, 0, 1, 0. Yes. So it is always good that we check the question one more time before starting answering, because it will help us to avoid mistakes of copying the wrong entry, because the only entries are zeros and 1. This now follows the usual matrix multiplication, a row versus a column, where we add the data. So how we go about it? This is 1 into 1 plus a 0 into 1 plus a 1 into 0. So this is going to be my first row, first column. This becomes my first element. How about the second element? Now shift your operator from over here to here. First row and second column. So what is going to be the matrix entry? 1 into 0 Next, plus 0 into 0 plus 1 into 1. Next, you shift your column for the third one, first row, third column. So what will be the matrix entry? 1 into 1 plus 0 into 0 plus 1 into 0. So my first three elements have been got. Now I have completed the first row, so I move to the second row. Now I do or repeat the same action with that of my first column, second column, and then my third column with my second row. Okay, so now the entry will be equal to your second row versus the first column. 0 into 1 plus 1 into 1 plus 1 into 0. Next, 0 into 0 plus 1 into 0 plus 1 into 1. Next, 0 into 1 plus 1 into 0 plus 1 into 0. And we move to the last row with that of the first column. 1 ones are 1 plus 0 1 plus 0 0. 1 0 0 0 plus 0 1. Last column 1 1 plus 0 0 plus 0 0. So now I can notice that we have a multiplication and a addition in this elements over here. Your multiplication is nothing but your AND operator, and your addition is nothing but your OR operator. We can notice that if at least one element over here in the product is going to be 1, then the input is 1 because it is your OR. So this is going to be 1 or 0 or 0. 1 or 0 or 0. So any one of them is 1. So the answer becomes 1. So this is 0 or 0 or 1. So any one of them is 1. So the answer becomes 1. 1 or 0 or 0. So now this becomes equal to 1. Next, 0 or 1 or 0. So this becomes 1. 0 or this is 1 into 0 is 0 or 1 into 1 is 1. So this becomes equal to 1. 0 or 1 into 0 is 0 or 1 into 0 is 0. Notice all the three of them are 0. I don't have at least one of them to be 1. All the three are 0. So what will be the matrix entry here? It will be 0 over here. Next, I move to 1 or 0 or 0. So this becomes equal to 1. This is 0 or 0 or 0. Again, see that it has all the three entries to be 0. So the matrix entry is 0. Now it is 1 or 0 or 0. So the matrix entry is 1. Be very careful, friends, not to add 1 or 0 to be equal to 2. This is wrong. And 1 or 1 is not equal to 3. This is also wrong. If either one of them is going to be 1, the marked entry is 1. If at least one of them is 1, the marked entry is 1. So whether you have 1 1 or you have 2 1s or 3 1s, the answer or the marked entry is always 1. In all the other remaining cases where you have all the three of them to be 0, then the marked entry is 0. This is how we do a matrix multiplication. I hope the working was clear. Now we move on to the last part called as MR square. Here it was RS. What is MR square? MR square is nothing but M of R dot R. So instead of taking the product with S, I take the product with R itself, then you call it to be MR square. So I have the problem to be MR product your MR. So it is 1 0 1 0 1 1 1 0 0, taken product with again the same MR 1 0 1 0 1 1 1 0 0. So you can do the matrix multiplication like our last type. 1 into 1, at least one of them is 1, so the marked entry can be taken as 1. You can just flip the remaining things because already you have a 1. Now move on to the next column. As a trick, 1 into 0 0, 0 into 1 is 0, 1 into 0 is 0, all the 3's are zeros, so the entry is 0. Next, 1 into 1 is 1, you have got a 1, so you need not have to bother about the remaining things. Next row, 0 into 1 0, 1 0 0, 1 1 is 1, so you have the entry 1. 0 into 0 0, 1 into 1 is 1, so you have got a 1, so you can stop. 0 into 1 is 0, 1 into 1 is 1, yes, we can stop. Now move to the last line. 1 into 1 is 1, yes, we can stop. 1 into 0 0, 0 into 1 0, 0 into 0 0. Now this has all the three values as 0. Next, 1 into 1 is 1, yes, I can stop here because I have got my 1. So this is going to be my matrix MR square. So we have defined the matrix of a relation R. That is how I can define a matrix on any given relation using the numbers zeros and ones. 1 if it belongs to the relation and 0 if it does not belong to the relation. We have done operations like complement and inverse, and also union and intersection and multiplication of matrices on relation. I hope this video was helpful for you to understand the concept on how to represent a relation as matrix. Thanks for watching the video. Happy learning and continue learning. Thank you.